There's one homework, which is a survey of the heart rate monitor project, which is this one. Did I show you this?
No.
Briefly. I need to write several paragraphs. Yeah, I didn't create this. It's required by the Purdue University's team. It's not an emoji, but very similar. Right? It's called photo voice. Instead of talk a lot, you put a figure in there, right? Sometimes the figure is not directly showing your emotion there, but for example, you show a tree or in the park. I don't know what does that mean, but you describe it, right? Things like that. Or you can show emoji if you want. So for each part of it, it's asking for three different figures, and with captions, and 200 words of the narrative to describe the experience over here. But I don't think 200 words is quite a few. Yeah, paragraph. 1, 2, 3, so total is 600 words. And these are, what are these? Interdisciplinary. These are some other kind of types of comments instead of your comments regarding the bio-inspired design, STEAM, and entrepreneurial integration, which is we put a push button in there, have all the bill of materials. So STEAM, science, technology, engineering, arts, just include arts in STEM. Then it becomes STEAM. So you did a lot of 3D printing design, that's everything about art. And also the flyer design. If you don't have flyer design, it's okay. If you did it, then you can talk about it that a little bit over here. Bio-inspired design. The entire project is biomedical engineering project, so no problem on that. Just so you understand how these kind of device works in the hospital. I have seen this a lot of times. Never know what is the theory behind the thing, but now you know how that works. And interdisciplinary, it involves mechanical engineering, which is a 3D printing, electrical, and also entrepreneurial mindset in there. You have to do the calculation and think about if it's profitable, right? A few comments in there. What went well, what didn't go so well, what we'll do differently next time. Okay, put some comments in there. So next time we can improve it later. So next year, probably I'm not going to do this at the very beginning of the semester because the funding is just for one semester. If I think this project is a very good one, I will definitely modify the code a lot. Instead of just letting students copy and paste, I'll put it as a just 2-week or 3-week project towards the end of the semester after they learn the fundamental programming first. Instead of directly jumping into it and copy and paste, so they're not learning too much because they require the survey results by March the 3rd. It's pretty much like 1 week from now. So we that's why we have to start it very early. So now we are almost done with the project, so you guys can do the survey. That's why I have to do it so early, which is not ideal. It's just required by the funding agency. Connect to the real world, no problem in this project at all. Okay, we got a PCB. We have we're making a product out of it. Everything is connected to the real world. All right, so that's the survey, and it's due Wednesday. So I have to, I probably can give you a 1-day extension to the 2nd of March because it's still 3rd of March. I have to send it to them by the 3rd of March. So, keeping my work on it and get it done before Wednesday or Thursday this week. That's one thing. All right, another one is a new tutorial starting from today, and it's due next Wednesday. Okay, you have a lot of time on it. And I looked through the tutorial one more time. Remember, this one is mainly about temperature sensors. You can see at the very beginning, it's a LCD first, because I have to use the LCD to display the temperature on it. That's why it's the LCD first. And then different types of temperature sensors. This is a thermistor. That's a resistor type temperature sensor. It's actually really compact. I definitely want you guys to try it. I have a lot in the drawer. If you couldn't find it in your little box, let me know. I have a lot. I bought a lot a few years ago. So that's a resistor thermistor temperature sensor. And I just found out that, this is a good one as well. It's just digital output as a good temperature to use. I hope you can learn how to do it. It has also temperature and humidity data through the one line, and then you can look at it from the serial monitor, and that's 8-bit for humidity, and then 8 bits of zeros as a separator, and then another 8-bit of Celsius degree and then Fahrenheit degree. Okay, that's from the one line, the data line. It's totally digital. Okay, so you can separate them and take out the bytes respectively and do the display on the LCD. You can see it shows both temperature and humidity. This is probably the cheapest and the one of the most popular sensor that has both temperature and humidity on the market. That's why I think you guys should learn how to do it. If you join a research team in the future, can be in the national lab, can be somewhere else, right? If they want to develop a test bench like the ones we are going to do in the summer, we're trying to test if the ionizer is effective to kill COVID. So in that case, we want to set up different environments for the humidity and temperature. So you need a feedback loop, but also you need a sensor to get data from the environment. So in that case, this becomes pretty useful, and you know how to do it, and you have some experience with it, which is great. We don't have too many sensors to use, right? Temperature, humidity, and have other ones, encoders like position sensor and IR sensor. Not too many. And I'm thinking this temperature sensor, which is a different one. It's a semiconductor based, all the transistors in there. You couldn't see the internal circuit, but like remember I told you cannot you cannot just turn it 180 degree. So it's going to short the sensor and make it really hot. That's why I put all these paragraphs here to let you know. But I'm thinking that you may not have this sensor in your box, and I may purchase a few of them a couple of years ago, but I don't know where is it right now. I don't want to spend the time, and it's totally unnecessary because it is a temperature sensor. Is this more accurate? Probably not. Is this more like convenient? I don't think so. It's even bigger than the thermistor. And why do we have to use? I've never used it for any of the research projects. So why do we have to do it? So you please don't do that. Okay. So skip this one. We are not using this one in this tutorial. Okay. It's totally unnecessary. Let's skip this one. And then come to the IR receiver module. It teaches you how to use a remote controller and also IR receiver, which is really fun because you have used this to control the switching between the TV channels a lot, right? And also we're going to use it to control the robot car as another 1 week project down the road. So that's why you need to learn how to do it, because this is not the only one we're going to use this semester. How to use a remote. Whenever you press it, it's going to show a code here, right? This code is a decimal being displayed on the LCD, but I think the number is like hex. Is that a hex? No, it's not a hex actually. As you convert it into a hex. So this is the decimal. You press it, you got a decimal number. And you convert it into hex to put it in the lookup table. So something like you have a table, I have a switch case statement, right? Whenever you push it, and if it's this case, then you do this, right? Something like that. It's just a very simple C++ structure. And remember, so this, whenever you have a remote like this, look like this one is not really reliable. Sometimes you push a push button, it shows a different code. And you have to try like 5 times, you probably got 1 or 2 of these attempts to be a correct code being sent to the sensor. It's really frustrating. I still don't know why they keep using this in the box. It's not working really well. So I'm gonna, if you have a remote like this in your box, definitely replace it with this one. You can compare the, these 2 different ones, you can see the difference. So this one has a little panel on the top, shows all the arrows for the 4 directions, and OK in the middle. So this one works way better. I think it's almost a 90% chance you will get the right code if you point it to the IR receiver and press the button. This one is pretty reliable, no problem by far. And we're going to use this one for the car later on as well. But also, I think Noah had a really good question last time. Can we use if we don't like the quality of this remote, can you guys just use the remote from home, the TV remote? I think it's fine, because every time you press it, you'll be able to see the code, right? Then you just write it down somewhere, and you put in the lookup table. So whenever you see this code, you know which key is being pressed and do a corresponding response, right? I think you can use either the remote of this one or the one you think has a good quality from home. It's okay. I have a lot of these ones as well in the lab. So that's how I convert it. You don't have to, this is not digital logic class. You don't have to divide by 16 all the time by 100 times to get a hex, right? So I always just use a calculator and change it to the programmer mode, okay? And you put the decimal number in there, right? So it's going to show you the hex number for that code. Make sense? So press it and you show it in the monitor, right? Serial monitor. So you know the code for each key, and then you put it into the case statement. Okay? And so now you see why we prefer hex all the time in programming. It's making the number shorter and a better look. I don't know why it's better look, but I just feel it's a better look than decimal. What do you think? I just feel better, right? You have one zeros in there, even though it's hex, but I know F is just 4 ones, right? It's very easy to convert it to binary instead of using a decimal number that I'm feeling bad for the computer because they have to convert it to binary later, right? But hex is just 1 zeros, right? In all these hex digits. And the next one is bare bone Arduino board. You have done that, which is great. Oh, you haven't. You haven't. You just put on the PCB, but you haven't practiced this on any of the breadboards. Because the Arduino Nano chip was a surface mount. That's why you didn't have the chance to plug into the breadboard and just try a bare bone controller instead of the Arduino board. Okay, so if you look at this tutorial, it has and the benefit of doing this is it's easier for prototyping purposes, because this Arduino Uno's chip is a DIP for 320, so it's 28 pin DIP chip. So you can plug this chip onto the breadboard and have this one. This is the oscillator instead of the one you used for Nano. That's the oscillator I have in the drawer. Definitely, you can find a lot in there. And 2 caps. I think the caps are 15 picofarads. The Arduino Nano's oscillator, the little tiny oscillator, has the oscillator and the caps. Remember the shape in the schematic? You have 2 caps connected to the oscillator, right? But this one doesn't integrate this. This is really old technology. It doesn't include the cap. So I have to put the two caps in parallel with this guy and to form that oscillator for this Arduino Uno board chip. The benefit of doing that is, you can test your code on the breadboard, right, with this bare bone microcontroller. When you build the circuit, you are directly using the microcontroller instead of the Uno board, which makes a lot of sense because this will be the final design to be put on your PCB, and you can test it on the breadboard. That's why you want to do it. But also, if you eventually you are trying to use the Arduino Nano chip, the surface mount microcontroller in the future, you can also test it using this dip version because it's the same die in the middle, right? It's if you take the chip out, the little silicon chip out from the package, it's the same chip, no difference. It's exactly the same pads and same circuits in there. So you can test it using this dip version because it's easy to plug into the breadboard to test the bare bone configuration instead of the entire board, right? Like this. So in this tutorial, definitely try that bare bone microcontroller with a dip version of the microcontroller. And keep in mind that many of these new chips are not bootloaded. And I think Connor designed another PCB board which can bootload these guys as well, right? So it's the time to test it. Okay. And now interrupts. It's another very important concept. It can be a bit challenging for now, but let's go through it. So we are not doing any other types of interrupt. Keep in mind, there are so many different types of interrupts. So you can use a hardware interrupt. For example, the pin, one pin of the microcontroller, for example, one of the pins is waiting for a trigger or stimuli. And whenever that one is getting triggered, it stops running all the programs in the loop and do that triggered project, the project that triggered that interrupt. That one has a higher priority. Like for example, it's a super emergency, right? Especially for the equipment being used in the hospital sometimes. So they want to run something different instead of running the routine loop. But this one is different. So we are doing the timer interrupt, which is whenever the timer is up, we trigger the interrupt. So we stop running that routine or stop running that main loop. We jump into a sub function. That's it. The sub function can be anything. You can define that sub function to do whatever you want, right? But it has to stop the main loop and jump to the sub function, being triggered by the timer. So you have to set up the timer, okay? And you can change the value in the timer to decide when you want to trigger that interrupt. Make sense? It's like a timer there. When time is up, you do something else. And then when that thing is done, you just come back to do the main loop, okay? So in that case, first I need to let the microcontroller know, I need to do all the setups in order to let it know we are doing the timer-based interrupt. So for example, here, this is what you have to do, okay? At the very beginning, you have to clean up all the previous interrupts. For example, it has some other different settings. You have to reset them, like no interrupts, and put a 0 here, 0 here, 0 here. And the first 4 lines are just for reset, nothing else. I just have to do it every time, okay? So just copy and paste the first 4 lines. And the fifth line is a comparator register. I'm gonna go through that, why we use this number very quickly. And this is another setting. So whenever you see this, it's pretty new to you guys, okay? So when you see this in Arduino or in AVR's programming interface, it means it's just setting this digit to 1. And why is that? So what does this mean? Like 1 being shifted by this, okay? So what does that mean? Let's see. So this is an 8-bit. So the microcontroller we are using is an 8-bit microcontroller, which means they have 8-bit registers, 8-bit memory banks, right? And so you can, let's find out this bit is WGM12. And these are all the snapshots from the data sheet. You can find them as well. But you can see that this bit is over here, right? And this is an 8 from 0 to 7, so this is a register in the microcontroller. And you can just imagine that this is just whenever you buy a new appliance at home, you need to set it up for a certain mode to serve you the best, right? It's the same thing. Before you start using this microcontroller, you want to do all the you want to configure it first. So these are the bits in the register which controls different functions. You have to turn on and off each bit in order to turn on and off that certain function, And it's being defined by the computer engineers who designed this chip. And they showed you here in the table what that means. So you can see these are the modes, right? And these are the name of the bits in the register, WGM13, WGM12, WGM11. And these are the, if you turn on WGM12, which is here, if you turn on this bit, you flip this bit. So if you don't do anything, by default, it's 0, right? Just keep in mind. You don't have to set up everything and put 0 in there if you don't want to use it. It's by default, it's 0, okay? So now we are trying to flip this one and to make a 1 here, and which is going to turn on some kind of function. Let's come back to this table. You can see if this is on, like WGM12, is this bit in this byte, right? In this register, which is the address is 0x81, right? It's a hex number address. So this address has this register, right? It's like a memory or register bank. And the bit 3 of this register, if you turn it on, it's going to turn on this function, which is called timer counter. It's called clear timer on compare match, CTC, which is this one. And match what? Match this guy. So this is another register. You have to put a number in there, okay? So which means you can define that number in this register to make the timer match to that number. When it comes to that number, it's going to trigger that interrupt. Any questions by far? Or questions are everywhere? So now the conclusion is so by flipping that WGM12 to 1, we are letting the timer or a counter, right, counts to a certain number and then trigger the interrupt. That's how it works. So count to which number? Count to the number here, the top, right? See, count to the number stored in this register. And you can customize it because you can put all different numbers in there, right? Just let it count to that number, then it's going to trigger the interrupt. So you can define how long or the duration between the interrupts, because you know the frequency of the counter. Make sense? Okay. So now I'm going to show you how to do the calculations. So see, this is a max number. It's going to count to 62500. Okay. I'm going to show you how we get it. Right. So by doing this, I'm flipping this bit to 1. And why is that? Yeah, so this bit in here represents three. Magically, you don't know why. The name here in that IDE, when you compile it, You understand this number as a 3 here. It's a bit 3. Okay, so it whenever you write down WGM12, it's being considered as a 3 in there. If you shift 1, so in the memory bank, right? In the 8-bit microcontroller, 1 means 0, 0, 0, 0, 0, 0, 0, 1, right? So this 1 is this 1. And you shift it by 3 times to the left, because 1 getting shifted by 3 times to the left, it's 1, 2, 3, it's getting this, right? So this is after shift. That's what you're getting. And this is the final result after the shift. And you OR it. So OR, you OR it with the original byte. You know, whatever byte you have here, right? This is TCCR1B register, and that's the byte you have. It's actually you shift the 1 to this position and you OR it to itself. What's going to happen? Yeah, so it doesn't matter what was there in the TCCRB, right? Doesn't matter what it had in the past. So it's OR itself. So if you have a 1, this bit will be set to 1. Definitely. Make sense? So what is this operation finally doing here? What is this one doing? It's flipping this bit to 1 in this register. So this operation is doing nothing but flipping this bit to 1, okay, to turn on this function. Same to the other ones. Let's see. CS12 is still in the same register, TCCR1B. Okay? And TCCR1B. CS12, CS10. Let's see. CS12, CS10. So these 2 bits are being flipped to 1. So it's 101 after the operation. It's a scalar. It's a pre-scalar, which means I'm dividing the original frequency of the clock by 1024 times. That's 101. I want to slow it down because the counter, I don't want it to come that fast. It's a 60 megahertz clock, even though it's not really modern technology, but it's still really fast. Okay, I want to divide it by 1024. You can do whatever you want, but you have to change the numbers later. But now let's just use pre-scalar as 1024. So I'm slowing down the clock, and this is a function. This is the equation I have to use to find out the interrupt frequency. So whenever you want to trigger with the duration between interrupts, and that's the function you want to use. So f clock IO, which is a 16 megahertz clock, you'll put a 16 megahertz over here, and 2 times n. What is n? N is 1024. That's a pre-scalar. You set it up by doing 101 here. Okay, that's how you configure it. If you put a 101 here, then n equals 1024. Okay, so that's how you get all these numbers. And then 1 plus this number. So what is this number? OCRNA is this one. It counts to this number, OCR1A. I remember when we flip WGM12, we're setting up the counter to count to something and then trigger the interrupt. So OCR1A is a number you put into the program, which is here, OCR1A. I put this number in there, you know, I calculated how I calculated, how I did it. Let's look at this equation, okay? Very simple algebra. All right, so what are the given numbers? What are unknowns, variables? And how we get this, because you guys are doing the programming, right? So you need to put a number in your program for OCRNA. Okay, is this one given? What's that? Yeah, what's that? Yes. What is n? How you make it? How you 1024? You set it up, right? You set it up by doing 101. Okay. Can I set it up 100 and use 256? Yes. It all depends your application. But sometimes if you find out you couldn't get a good number or something, a lot of times if you make a very small number here, then you got a big number here. It can be, if the frequency is too big, which means it's just too fast, right? You have to change this number accordingly. But this one is a 16-bit number, so it has a limitation in there. 16-bit, I know it's pretty big, but sometimes you have to adjust this number to make the best use of this 16 bits over here to get you a desired frequency of the interrupts. Anyway, so so now we have this one to be 1024, and this is given, which is 60 megahertz. And now we have two variables, right? Two variables. And this is the one we want to put into the program. The OCRNA is the number we want to put in the program in order to make up a certain frequency of the interrupt. Right? Because the certain frequency of the interrupt is something I want to realize to the hardware. Okay, so that's why you need to find out this number. Okay, so when you do the program, how do you get this number? Yeah. Yeah. So the left side of the equation, right? Yeah. You have a desired frequency of the interrupt. So it's given. It's not given, but it's known, right? You know it. And then you calculate back to find these numbers and you put in the program. Make sense? Okay. So now look at this calculation here. 60 megahertz divided by 2 times, give it 2 times 224 times 1 plus, okay? 1 plus. I don't know. It's just from the hardware. I don't know the digital design, what's happening in there, but just use it, okay? 1 plus that number, and you are getting 0.125 hertz. Okay, so that's the 0.125 hertz. That's a digital system, which means it's a square wave, right? So this clock here is going to be 0.125 hertz, or we can say the period of that square wave is 8 seconds. Okay, so after you do this signal becomes 8-second signal. So a square wave becomes this, right? And the entire period here is 8 seconds. Okay, one thing you want to keep in mind for this one period, you have one floating edge and one rising edge, right? For each period. And you're saying you got another floating edge here. No, this floating edge belongs to the other signal, the next period. Okay? So one period, you got one floating edge, one rising edge. Make sense? Okay. So for Arduino, both the rising edge and floating edge will trigger the interrupt. Okay, just remember that. That's designed by the engineer. So, quick question. How long it takes to trigger each interrupt? Yeah. Okay. So by design, by putting in your program, right? That's everything you can control. By putting what in where, you are getting a what frequency for interrupt. Then you have a 4 seconds interrupted period or duration. So every 4 seconds, it's going to trigger the interrupt to do something. Okay, so in this project, every 4 seconds, it's going to trigger the temperature sensing, and it's going to update the temperature, which makes sense, right? 4 seconds, you don't want to up the temperature every 1 millisecond. It's not changing that fast. Like the room temperature, it changes. I mean, do we really need to sense it to update it every like 4 seconds? Probably even not 4 seconds. You can update it every like 30 seconds, right? But let's just update it every 4 seconds. You just trying to see if there's something going wrong, right? If the heater or the ventilation is down, like we trigger that temperature sensing every 4 seconds, will definitely do the job. Okay? Make sense? So that's the main part of the interrupt we're going to learn this in this lecture. Okay, and all the rest are just showing you all the registers. You can see the addresses of the registers. But the good thing about Arduino is in the IDE, you don't have to deal with each single bit all the time. So I think this is probably the only one chance you're accessing the bits in the Arduino registers. We haven't done that in the past, right? But you guys are lucky because back to like 20 years ago, when I was in college programming all the microcontrollers, we just have to configure every single byte in the register all the time. That's from the microchip microcontrollers, so PIC microcontrollers. That was super popular by that time. But every time you start doing anything on the top, right, it doesn't like set up, right? You have a pin mode and just set it up, just programming in English, right? We have to do all the bit set up all the time in order to make it running in a certain mode. So that's why microcontroller was not super popular among all these hobbyists and beginners until probably 10, 15 years ago, when the Arduino gained the momentum because they have all the libraries available for students to program. It makes it super simple to work with instead of all the other ones. And nobody, very few people are still playing with the PIC or other like TI microcontrollers anymore. I think Arduinos are one of the most popular ones. The ST32s and also the STM32s are also very popular. Okay. So how to access the bits in Arduino's register? How to access the bits? Could you change the name of this variable? Let's say I call it TCCR1E. What about that? No, these are keywords. These are the name of the registers. Cannot change it. Keep in mind. But never name any other variables the same name as these ones. These are the registers. So whenever I put this in here, it recognizes as a register. It's going to access to that address and modify that register. Okay? So how to access the bits in this register? How to access the bits? Yeah, that's it. Right? Put a 1 here and shift a 1. It's really weird kind of programming technique, but that's how it's being used in these AVR microcontrollers. So you put a 1 in there, which is a constant, and you shift that constant to a number of bits to the location of that bit. And then you OR the original register to make it happen. Okay, that's how you access the bits in the register. Okay, and this is the ISR, and this is the flag. Okay, so you don't have to program the very bottom level of the things. So whenever the timer is up, it's gonna set this flag, this vector. Okay, and it's going to enter this ISR, which is interrupt service routine, okay, ISR function. So what you need to do is just in your program at the very bottom, create a subfunction, and the subfunction's name has to be ISR. You put an ISR parentheses timer 1 is a compare to match, right? That's what you did, and vector, that's what you have to put in there, and then do the temperature sensing or display or whatever. You can't in a curly bracket. Okay, and what I remembered from last time was the DHT11 library has a conflict with the interrupt, the timer one interrupt we have. So which means if you use a library, from the code I provided on the website, it may have a conflict with the timer I set up here. May or may not. I forgot. But let's see what's happening here. So use a barebone at Mega to build a portable digital temperature meter. Use an interrupt service. So you can use the temperature humidity sensors. You can use any you don't have to use this temperature sensor, okay? Let's do that. You can use a thermistor. It doesn't matter. I don't really care. So you can use a thermistor and then display the temperature on the 7-segment display. Okay, so this can be a bit challenging. Sounds like a really easy project because you are showing numbers on the 7-segment display. Remember how that works? The 7-segment display has to be scanned to make it show the digits on the different units, right? So you scan it, you have to use the same time delay for the to activate each unit. If you use a different time delay, then it's not showing a number in the even brightness. It's just super odd. So what I mean is you have a main loop to loop through all the time delays or activation of the units, but you still have to do the temperature sensing, how to manage that. Does that make sense? So for example, you have a loop. This is a loop, right? It's the loop, all right? And you activate, you have 4 units of the display to display temperature, right? That's a 7-segment display, okay? You have to activate each one each time and throw a number in there and then move to next, right? Okay. So you activate the first one and you display it. And you activate the second one, you throw a number to it. And you activate the third one, you throw a number to it. You activate the fourth one, you throw a number to it. Okay? And then the loop in the microcontroller is going to come back to the top and then activate the first one, throw a number to it. It's just running the process super fast, where I cannot resolve it. It looks like a static number on it. Okay? However, if you do not use that interrupt, where should you plug in that sensing code, temperature sensing code, which takes a lot of time? You know what I mean? The time delay in between is evenly distributed. But if you plug in, for example, plugging a temperature sensing code here, right? That's where you want to update your temperature. So it's going to make the time delay in between the different units uneven, which means it takes a longer time for this unit will make it dimmer or brighter a lot of times. It's going to show a really weird display. Okay? So how to do it? You can show the display time. So what I did in one of the projects, prototype, I did it for a company. So you can keep running the loop back and forth, use an even display or the same display in between these activations. Just keep running the main loop. And then you have an ISR here, right? And you only trigger it each 5 seconds. So in that case, during the 5 seconds, you have a pretty good display, okay? But after that, it's going to trigger the interrupt and do the temperature update, okay? And then it's going to come back to the display by itself. So you are not interrupting the display all the time. you only interrupt every 5 seconds, which is fine. Because 5 seconds, your eye will, receive a lot of photons from the display, and you recognize that's a static number in there. So it's not changing. But after 5 seconds, it triggers the interrupt, the ISR, and then it's going to update the temperature, and then it's going to come back to all the things. Again, so you are not interrupting the display in the middle, but you interrupt the whole thing every few seconds, which is fine. And then what's going to happen is it has a static temperature. Every time it triggers interrupt, it's going to blink. So all the 4 digits are going to blink. You know what I mean? It's going to blink and then update it to a new temperature. Okay, let's get there first, and then we are going to talk about how we can get rid of the blinks from the displays. I think you can. So before it triggers the interrupt, right? Whenever it enters the interrupt, you can just assign that temperature right before that, right, to a certain thing, to a certain variable, and how to hold the value in there, right? That's probably something I have to think about. It's okay if it blinks, right? We'll figure out, how do we avoid that later. Any questions by far? Are we using the DHT11 temperature sensor for this project, for this task 9? No, we're just using thermistor. Why? Because the DHT11's library has a conflict with your interrupt library. Okay? Questions? No? Are good? Yeah, what about the printing? Have you started? Done?